Hello and welcome to the eLab Innovation Podcast, the podcast on e-mobility for research and industry. My name is Simon Voss and I'm the Managing Director of eLab of RWTH Aachen. And today I'm excited to welcome Professor Dirk Uwe Sauer, one of the most renowned experts on battery technology, here to the eLab Innovation Podcast.
And in batteries, first of all, it's quite similar. Yeah? So for sure, we have still also increase in energy densities and so on. But what was most important to make it really applicable to electric vehicles is a reduction in prices. And here as well, in 2012, in 2012, the predictions by industry and others for 2020 were about 200 euros or dollars per kilowatt hour. On cell level in 2020, actually we were down to half, down to $100 per kilowatt hour.
Okay, Professor Sauer, thank you very much for coming to eLab today. I'm looking very much forward to the conversation. So I think there is no real need in order to introduce you, but maybe we do a little introduction anyways, to just give the audience some information on who you are, what your trajectory into the battery world currently is or was. Where should we start in order to understand how you built up all the battery competence over the last years or decades?
So maybe when I started searching for a study course, I chose physics at the end of the day because I was sure it was necessary to do something for sustainable energy. So and then I started to study physics, and then I was lucky to be able to do already my diploma thesis and then also my PhD at the Fraunhofer Institute for Solar Energy Systems in Freiburg. Started more than 30 years ago, and with this I started right away also into the energy storage topic because we worked mainly in these times on off-grid power supply systems, because this was where photovoltaics was already in the 1990s or early in the 1990s the most economic solution for small appliances like parker ticketing machines, which we all don't like, but which all use PV these days, and for sure a battery, which nobody sees, but which is obviously there.
The solar cell is visible, right? But the little battery underneath.
Absolutely. But we also had applications in the Black Forest or in the Alps, alpine huts with autonomous power supply systems, and we had also the first
because of the location that was
remote, exactly. So several kilometers,
decentralized power supply,
several kilometers away from the next power connection, and cables are extremely expensive. But I worked also during my PhD in the first self-sufficient solar house. So a house where really a family lived, using PV and good insulation, but also hydrogen. So we generated hydrogen with electrolyzers in the summer. We stored it and we used it in the winter for heating and for cooking and for power generation. And for sure, I worked on the battery in there. So this was a great vision of Professor Goetzberger, who unfortunately just died 10 days ago. I think he's one of the greatest pioneers in Germany. So he started in 1981, the Fraunhofer Institute for Solar Energy Systems. Already it was the 4 departments on buildings, heating in buildings, hydrogen, photovoltaic technology, and system technology.
Oh, wow,
So this in 1981.
So all under one chair?
All in one institute, for the Fraunhofer Institute, which he then made up himself. And this is the school where I'm coming from. And then I worked since 2003 at the Fraunhofer Institute, also then going over to grid storage technologies. And then, since 20 years I'm here and looking into batteries especially, but also generally to the question of energy storage in the context of what is necessary for the Energiewende to work against climate change at the end of the day.
That's our common goal, right?
Absolutely.
In terms of power generation or energy generation, and then the usage, and there on both ends we are always confronted with the topic of batteries.
That comes along, but nevertheless, I always say energy storage should be installed only to an extent which is really needed. So in terms of renewables, we have to increase the capacities more or less on infinite.
The generation capacities.
Generation capacities. But energy storage should be limited to what is really needed, because it always adds additional cost. It causes additional losses. It also consumes a lot of raw materials. So we have to be. We always have to look what are alternatives. So energy storage is. If you use flexibilities, so in the future we will have a lot of electric heating systems, for example, heat pumps, direct heating, come along with a lot of water-based energy storage for heat. So this is a perfect measure also to balance the electricity grid.
Yes.
And if we can go for these type of flexibilities instead of setting an additional battery.
So you mean, just to clarify, you mean like with the balancing on a like short-term basis, on an hourly basis, where you can compensate the fluctuations of the daily energy demand?
Absolutely. So let us call it short-term storage. So everything which allows leveling of fluctuations within 24 hours. This is what we can do with charging or not charging of electric vehicles, with PV home storage systems, but also with the heat systems, and also the industry. The industry becomes more and more flexible. And with all the digitalization, we are also looking into in the energy sector. I'd say we probably will see something like the high-speed trading on stock exchanges. So energy, as soon as electricity price rises, especially industry will reduce the power consumption. At the price falls, they will increase, and all this is from a grid point of view, from a grid stability point of view, is similar to energy storage. And therefore we have to have the perfect mix at the end of the day.
So I think that's important to just note. We have on the demand side, management side, we have variables that we can set, and on the technological side as well. The one is like through the means of the mechanisms of the market, we can regulate or even out certain spikes because prices go up. And then, as you said, from the industry, it will be used less. And then they will maybe shift to the night and use the energy there. And then on the technological side, we have batteries in place, which can also buffer. And this could be a business case as well, of course, where you can have a battery storage farm and then storing the energy when it's cheap and then releasing it or providing it to the market when it's more
absolutely, but it is all on the marketing competition. So in the market, operating a pumped hydropower station, which can do nothing else than storing energy, is in competition with shifting or of charging processes of electric vehicles, or of these ramping up and down of industrial processes. From the grid perspective, from the energy market, this is all the same. And this is why this is all in direct competition. So also one of the reasons why nobody really is planning new pumped hydropower stations anymore, because they also just deliver energy or power in the same way as you can provide it by electric vehicles, as an example, or by managing the heat sector. And with the disadvantage that you have to pay 100% of the cost have to be refinanced from the energy trading, whereas an electric vehicle, you just have to cover marginal costs first of all, because the people buy the batteries because they want to have the car.
Yes.
And therefore, it's difficult to have such storage systems which doing nothing else than energy trading at the end of the day.
Okay, not diving too deep into this discussion right away, because I just wanted first paint a little bit the broader picture as well. But just a short question, because we're anyways discussing this right now. You mentioned pumped hydropower. In terms of the famous dollar per kilowatt hour or euro per kilowatt hour, also on long-term storage, if I want to store it for more than one day and then look at it maybe even seasonally, if that is of any use or market use later on, but is the battery technology already reaching the same price per kilowatt hour in terms of storage?
Compared with the pumped hydro? No, yes, it does. Okay. But the pumped hydropower stations are also not made for more than a day. So our pumped hydropower stations in Germany have at full power 8 hours of energy, not more than this. And they also work on a daily basis. The energy storage can earn money only if they work. Only if they're doing cycling, they earn money. And if you have an energy storage system, for example, which can supply for a week, then you can sell once in a week, and then you have to recharge. So you have every 2 weeks a cycle. You cannot earn money. So that's a big problem. And just as a last idea maybe on this, the electric vehicles we have on the road at the moment in Germany, in total something like 1.8 million full electric vehicles and plug-in hybrids, already have a battery capacity in the range of 75 gigawatt hours. All our pumped hydropower stations have 40 gigawatt hours.
It's almost double.
It's almost double now. And we have 48 million cars. Not even 2 million are now electric. So you see the huge capacities which come. So if you only use 5-10% of this, you have you double, you triple, and more the existing capacities.
Okay. I think that's a quite good motivation and clearly shows the potential that batteries and electric vehicles have for energy storage, not just for mobility, but as a second
for sure
use.
The primary use is mobility, but
but
in addition, this is yes.
And that and it's relevant for every household in the future, I think. So before we go more into the technical potential that is there for battery technology, and also the challenges and what we are researching and testing out, etc., currently for the mobility and energy storage for tomorrow, let's have a more broader perspective first, in terms of climate and in terms of what we have to do in order to meet the goal. And there my first question to you is, like, there was a goal of 1.5 degrees to reach that, or not, to not exceed that. Do you think, looking at the potential of battery technology, because it's a central element in order to reach that goal, are we able to meet that still, or should we aim for a more realistic target? From your perspective, I mean, there is no final answer, but
there is a very clear answer. We will not meet the 1.5 degree centigrade target, which was for the first time mentioned in the Paris climate conference. This is very clear. If you talk with the climate researchers, we are already there. So there's something has to do with some hidden energies which are already in the atmosphere and so on. So there is no pathway at all which allows us to get it down to or to keep it at 1.5 degrees C, at least not now. So maybe towards the end of the century, if we are going into negative emissions and so on. All the climate models say that we need significant negative emissions, which means we take actively CO2 out of the atmosphere and we bring it back under the Earth, latest from 2040 onwards, and then we may go via a maximum in temperature wherever it is. So even 2 degrees will be hard to achieve, but we can lower the temperature then again by massive negative emissions
through CO2 capturing.
By
one
CO2
thing,
capturing.
and then I think the second one would be easy, growing trees, or
this is one part of these technologies.
Part of the solution plan there.
Which is, it's not very clear if this really works. So because at the moment, due to climate change, we have to make sure that we even keep the amount of forest we have. So if we look the drought we have also in Central Europe, like in Germany, we must assure first of all that we keep the amount of trees we have. And anyway, this is just an intermediate technology, because after some years, maybe 100 years, the trees are dying and then the CO2 is emitted again. So this helps for a certain while. So it helps for a certain while. But it is one of the more or less 6 different technologies which are mainly looked at for negative emissions, and for sure growing crops and trees is one of them.
Okay, so that would be on the subtraction side. And then we have, coming also soon back to the battery technology, but then on the generation side, we have the potential to lower our emissions, right, by sustainable technology. And I think by 2030, we should be about 80% renewable. Is that?
80% renewables in the electricity sector. Yeah? But so
that's only a fraction, right?
But yeah, simply speaking, Germany had in the past something like 3,000 terawatt hours of primary energy demand, and 600 terawatt hours is electricity. Yeah, so and out of the electricity growing, we now expect
so a fifth of the total demand.
A fifth of the total demand, whereas with electrification, for sure, we reduce the demand dramatically. Yeah, because if we go for battery electric vehicles, for example, we reduce the primary energy demand roughly by a factor of 4, and if we go with heat pumps into houses, maybe by a factor of 4 to 5. Yeah, so we must not replace 3,000 terawatt hours, but at least something in the range of 1,200 to 1,500 terawatt hours. And now when we talk about 80%, right now we have about 50% renewables in the electricity sector. We have, I think, 5 to 7% in the mobility sector, and 10-12% in the heat sector. So this shows where the problem is. We developed very well in the last decades power generation technologies like wind and PV mainly, and this will be the core of the future energy supply. But we have to be aware that we have to generate, for example, for the organic chemical industry. Organic chemical industry in Germany uses about 18 million tons of oil per year, not for energy purposes, but as a raw material.
For the chemical industry.
For the chemical industry. Worldwide, this is 500 million tons. And if we want to operate our chemical industry further, we have to generate artificial fuels, e-fuels, you may call it. Yeah, so this is at the end of the day, it's oil products from hydrogen, and just for this we would need roughly 3/4 of today's power generation is just needed to generate the fuel or the equivalent for the chemical industry. Yeah, so this shows a little bit the size of the problem we're going for.
Yeah, and I think that opens a very, very critical discussion that is going on right now. Right, because e-fuels, I think just recently it's also quite debated in the media in terms of e-mobility, but not touching on that right now. But so you mentioned hydrogen for the chemical industry, which has to be generated. Does hydrogen provide a general solution, an overall solution, let's say, that provides, as you say, for the chemical industry, but also, because some are debating that as well, for the mobility sector. And that can be differentiated in cars, electric vehicles, but also trucks and the whole commercial transport sector. And I was just last week on a conference on non-road mobile machineries, so the whole construction sector, agricultural sector. Do you see, as some propose, hydrogen be a solution there, or would you differentiate? To touch on hydrogen first, and then we come to e-fuels in the second, before we return to pure battery-powered vehicles.
So first of all, I think we talk about hydrogen or e-fuels or whatever. This is more or less the same, yeah. So this is just some conversion in between, yeah. But it's always, first of all, you have electricity, then you make hydrogen, and then it's just a question: are you processing this further, for example, to ammonia or to methane, or you take Fischer-Tropsch procedures and you make liquid fuels? Yeah?
So and then use that for chemistry or
right. And to be honest, I don't know really if the airplanes in the future will use direct pure hydrogen, or if they will use an ammonia or an carbon-based energy carrier. Yeah, so hydrocarbons, an e-fuel. Yeah. This is maybe open, but at the end of the day, it all comes from the electricity generation first, then hydrogen. So that therefore, it makes absolutely sense to look in all these different fields you just have mentioned individually. And I totally agree that if you build a road somewhere far away, this will not be the excavators or the machines will not be operated on batteries. There's simply no grid out there. Yeah? So this
even though if the battery technology will advance much further,
even then, so because they are working 12, 15 hours, heavy loads, so. this is not really what you would like to operate with batteries. It's something different if you build something in city centers. So cranes, for example, always were electric. And it won't be any problem to have all the other machineries in the city centers battery electric driven, because we have easy recharging opportunities. On the other hand, if we go to farming, for example, so if you have harvesters, so harvesters in the autumn, they run maybe 24 hours a day, 7 days a week and more, and they are far away from any infrastructure. And in addition,
so for farming crops, right?
For farming,
so everyone is not
for harvesting, for harvesting, and there is no electricity infrastructure for fast charging out there. And in addition, the farming machines should be quite light, because otherwise they compress the soil, which is negative for the soils and so on. So they will need a biofuel or an e-fuel or something like this.
Hydrogen would be a solution?
Yeah, hydrogen is direct hydrogen maybe, but it is difficult to handle. So this is just a matter of technology at the end of the day. I would see more liquids in these cases. But this is not so, from a systems point of view, this is not that important if it is directly hydrogen, because as I said, at the end of the day, making from the hydrogen an e-fuel costs another maybe 20% of efficiency, but finally, from a systems point of view, it doesn't matter too much.
So I think that there the criteria then would be the technological feasibility. So if I am able to provide the same service, the same function, like the harvester on the field, regarding the current application or the current requirements that are needed in order to harvest efficiently and fast, etc. So on that end. But I think the further we go towards the city center, so from the remote area, and the further we come down from the energy intensity. You mentioned the harvester, which is one of the, I think, most energy intense machines that are there. In the agricultural sector especially, and then there are also similar machines in the construction sector. But the further we reduce in size and the further we come back to the city center, there will be a point where it's not about the technological feasibility, but about the economic viability, right? Because then we come back to the conversion efficiency that you pointed out, and where the economic decision will be made. Or if we use hydrogen, if we use e-fuels, or if we use direct battery technology, because for those applications, batteries may be sufficient in terms of energy storage and charging availability, the charging infrastructure.
The difficult thing is it's the economic thing on the one hand, but it is also, and this is something which is really overlooked in many discussions, for probably at least 20 years, hydrogen and all the products we can make from hydrogen. So if I now say hydrogen, I mean everything which comes behind e-fuels or whatever, will be a very rare element, because the worldwide capacities are almost zero today to produce it. And it has to be ramped up, but it has to be ramped up in really huge scales. So the International Energy Agency, for example, predicted that the electrolyzer capacity has to increase from now to 2030 by a factor of 2,000. This is quite a bit. So a factor of 2,000. So. That's a long way to go. And so this is the reason why in some cases I say very clearly this is an application for hydrogen, and this should not be an application for hydrogen now. Not because it is not, it cannot be used or it makes no sense from a technology point of view, but if we have a limited resource, we have to make decision. Exactly. So. And when we talk, for example, with industry, especially in Germany, but in other countries as well, if they have to become CO2 neutral, or if they have problems in getting sufficient energy, for example, of the gas crisis we have, natural gas crisis anyway, we have to offer them options for their future business models. So we may need, if we want to have the organic chemical industry in Germany, we have to offer them an alternative to the oil they are using today. And as I said, 3/4 of today's energy production, power production in Germany already goes into this sector.
So we have to allocate the resources where they are best applied.
Exactly. And so this is not necessarily the one where it is most, or the question is always what is economic. From the business point of view, it is most economic where you can earn most, or where you get the highest value for your hydrogen. Maybe this is somewhere else. So if we look to the mobility sector, for example, if the gasoline prices rises from €1.50 to €2, this has almost no change. So people just pay. So this is one of the reasons why so many people try to get into the mobility sector, especially for the individual cars, because they assume that the people are willing to pay high prices. And then this is a big discussion.
So for hydrogen then, I mean, it's price per energy. And the question is, what is the value added that I can achieve by using this kilowatt hour in order to fuel a car? May it be by batteries or whatever, then it's the price per kilometer. But then the calculation that also has been conducted is the price per energy for an alternative use in terms of hydrogen, as you pointed out. The added value may be higher in the chemical industry then, if I make some chemical product out of it. And then it will be, as you said, driven by an economic decision that hopefully will sort out where we will find hydrogen powered vehicles or mobility, or because hydrogen is used better elsewhere, if they will be less because this hydrogen is then used in the chemical industry because it provides more value.
But maybe the chemical industry is not willing to pay the same high prices as a mobility sector, because at the end of the day, they, at least at this point in time, they may decide, okay, if the hydrogen is too expensive, I go somewhere else where I still can use natural gas, for example, to the United States, which I get at a very low price. The competition there is worldwide, so it's not that easy to shift such a production. Nevertheless, it can be done on a medium-term time scale. And so this is why we need, at the end of the day, what several people don't like too much, but we need we need political decisions, which is more important for us. And I say passenger cars don't need hydrogen because we can provide mobility more or less in the same way as we have today without hydrogen, and we can do it much more efficient. And this is why simply this is not the sector where we should introduce hydrogen or e-fuels, at least not for new cars here. Whereas in the chemical sector, if we want to have this, we have to provide sufficient energy. And this is the same for steel manufacturing, this is for glass manufacturing, and many other fields, all the fields where you fertilizers, which then produce as an intermediate ammonia. So ammonia will be the first product, hydrogen-based product we will import. So this is quite likely it will come from Saudi Arabia. Probably maybe in 2 years from now already, electrolyzers and PV and wind systems are now under construction, and then it will come as ammonia. But it makes no sense then to extract the hydrogen again to feed it maybe into the gas grid for space heating. First of all, we should use it where it has the highest value, and this is using ammonia as a pre-product for fertilizers.
Yes, I understand.
Because today we take natural gas, we extract the hydrogen from the natural gas, so we have the emissions, CO2 emissions, and we have the anyway high prices for the natural gas at this point in time. But this is where one has to look very individual. So airplanes, I say during my lifetime, you will not fly in a passenger airplane to the United States on batteries. Simply too heavy, and there is no route within which we see as an option. So it needs other type of fuel. Could be hydrogen, could be ammonia, could be methane. could be e-fuel. So, but hydrogen-based materials.
Yeah. So looking again at the scale, right? The bigger the machines, the longer the range, the less likely it becomes being battery powered. But as soon as it becomes technologically viable, it's very likely to be battery powered.
Yeah, but it's not that easy. For example, the heavy trucks. Yeah, so the heavy trucks can go on batteries as well. Yeah, so because they run along infrastructure.
Yeah, because
that's a point.
This is like the remote part again. So there's the infrastructure where we can provide charging spots.
Yeah.
I think, and as well, the right logistics in terms of there's this lunch break or like at such points where we can charge again, right?
Absolutely. After 4.5 hours, the drivers must make a break of 3/4 of an hour.
Yes.
And with a 1 megawatt charger, we can recharge the battery. This is from a battery's point of view not even a challenge because it is 1 C rate, roughly what we say. So this is significantly less challenge than doing ultra-fast charging of passenger cars with 350 kilowatts because the batteries are much smaller. So the wear is significantly higher.
Yeah. Is there a limitation on the grid side currently when we think about, okay, the megawatt charging is a big point. Also in the NRMM sector, as I was mentioning earlier, people are discussing this quite a bit. So if we want to roll out the megawatt charging, which allows us, I think, to refill, like, as I said, within 45 minutes, or if you take 1 C within 1 hour, of course. Is that a challenge currently to establish the grid to let all trucks be refueled by megawatt charging in the lunch break?
So it's two different questions. The question is the grid connection, and for sure the grid connections to the highways where we can recharge the trucks is not existing yet. Yeah? So this means we need at least a medium volt connection, high power, 20, 30, 40 megawatt of connected power, maybe more, depending on how many trucks we have to recharge per hour. Yeah? But so this needs to be built. Yeah? So it needs to be connected to the next high voltage line, typically 110 kilovolt, and this is needed in addition. Anyway, no question about this. Possible, yeah. So this is not the main challenge. And
also, given the time frame, if we think of the next 5 to 10 years.
So just a matter of will. Yeah.
Okay,
so
good. Yeah, it's
no,
good to know.
that's absolutely possible. And the trucks, at the end of the day, from a grid point of view, are less of a problem than the passenger cars, because for the grid, the problem is always if you have peak loads. Yeah. But the trucks will consume more or less continuously power. Yeah? So we have 24 hours, 6 days a week. We have the trucks running on the highways 52 weeks a year. Yeah? So this is a relatively continuous load overall.
So the lunch break will not be always at 12 o'clock. That's what you mean, right?
No,
it will be around the
all.
clock, shifted, because there are different time schedules for every driver.
But it's the same today, yeah, because the trucks cannot stop all at the same time. Yeah, you see what happens during night or during weekends if a certain number of trucks have to stop there, then already all our parking lots are crowded. Yeah?
Yes.
So no, this will automatically shift, but this is is a normal distribution. Yeah, because passenger cars is more of a challenge, yeah, because there we will have peak loads. For example, when in the few weekends when people go on for holidays, yeah, then you will have all the fast charging stations on the highways under full load, yeah, whereas the rest of the year the usage will be significantly less,
it's more distributed,
and then you have to provide sufficient power generation capacities and also the high voltage grid capacities to serve really these weekends. Not a major problem from a technical point of view, but it's an economic point of view, because you use the infrastructure significantly less.
Okay, so I want to pick up one argument or one idea that's also put out there quite a bit sometimes, because of such peak loads. One may argue, but we have the existing infrastructure of gas stations and potentially be able to, coming back to e-fuels and hydrogen for a second, be able to use that infrastructure in order to shave those peak loads or to provide alternatives to not face those bottlenecks in the energy supply. Do you see that from a practical point of view as a potential solution, as a valid argument, or would you say, yeah, we have a bottleneck there with on holiday season, everyone starts their journey into holidays at the same time and wants to refuel? Yes, but still it's not a really sustainable solution using e-fuels and hydrogen for that matter.
You're not talking about the passenger cars or the trucks?
Well, everything that's on the road.
So there have been studies already done by some truck manufacturers already years ago, and they came very clear to the conclusion that the future of the heavy trucks will be batteries, for different reasons. First of all, they said they think it's easier to roll out this all over the world because trucks is a world business. So the number of trucks for sure is significantly smaller than passenger cars, but to achieve good prices, you have to have products which can run all over the world. And for example, if you go to Africa, it seemed to them significantly easier to drop more or less, and the recharging station with a huge PV generator and then a stationary battery.
And to build up a hydrogen infrastructure.
No, not a hydrogen infrastructure.
Instead, it's easier to build a battery infrastructure.
It's much easier
than a hydrogen. Okay.
Much easier. Significantly less problems, especially because also for trucks you should consider liquid hydrogen as a fuel. Otherwise, the volumetric energy density is of a problem. This is one thing. They think it's easier to roll out electricity-driven trucks worldwide, and the other one is economic, because they said roughly in a heavy truck in Central Europe operation, from the life cycle cost, it's about 45% which goes into energy. So it's only 55% which sums up maintenance, investment into the truck driver payments, and so on.
Wow.
45% goes into energy.
Okay.
And the margins you earn are very small. So the question is all about the cost of the fuel. And as we need 2.5 times more energy with hydrogen with electricity. So at least if we assume that this is not somehow unfair or unbalanced has taxes in an unbalanced way, hydrogen must be more expensive as an energy carrier. Even if we import it, then we have the import cost on top, and if we have to liquefy it again, and so on. So no way to get the same price. And this is why they say, from an economic point of view, it must be electricity and batteries.
Okay.
To be honest, there's for sure other large truck manufacturer which still claims that hydrogen is a solution. For what I don't know exactly what their main arguments, but when we look to what really happens, so one of them now said, okay, as an intermediate, we will build battery electric trucks before we may go to hydrogen. But this is something I don't believe at all.
And I don't understand that. Because you provided the kind of perfect segue to the thrilling question I have in order to let's provide an overview, because you said already the conversion efficiency, but let's put that side by side, right? So on the one end we have battery vehicles and the whole generation to usage chain, and then hydrogen, and then for the completion, let's look at e-fuels as well. How do they compare? Just to put that in perspective, because as you said, batteries as an intermediate solution, and then switching back to a technology which is less efficient in its overall energy use. So let's frame this a little bit and give an overview on that. I think
first of all, we can look to the efficiencies.
Yes,
so roughly speaking, or what you can analyze not only in mobility sector is if you have a kilowatt hour of electricity, the question is how can I save most CO2? And the first measure is to turn down a lignite power plant. This gives you about 1.1 kilograms of CO2 per kilowatt hour of electricity. So second is turning or replacing an oil space heating system by a heat pump. So this also gives you more than 1 kilograms of CO2 savings. So, but if we compare the mobility things roughly with hydrogen, you have a factor of 2.5 more energy demand, or you save 2.5 times less CO2 for the same kilowatt hour of electricity. If you go to fuel cell e-fuels, you have maybe a factor of 6 with battery electric cars.
Mm-hmm.
This is the one thing.
For the same fleet, you mean?
For the same car at the end of the day. Yeah? So if you drive a passenger car of a certain size with battery electric compared with e-fuels, then you roughly have to provide for the e-fuel 6 times more electrical energy first of all, to make
so relative to the battery vehicle or relative to the status quo of combustion engine?
No, relative to the battery vehicle.
Okay, wow.
This comes along. First of all, you have to produce hydrogen, has a limited efficiency. Then you have to convert it into the e-fuel, and then you have at the end a combustion engine, which has 25 to 30% of efficiency. You can easily calculate that the overall efficiency cannot be very high. So
you end up at something like 30%. Or
less, So
less.
if the efficiency of the average
combustion
engine is 25%,
if we can dive into this briefly, what are the conversion efficiencies? Can you give us
roughly the electrolyzer is 75%, and then to make an e-fuel from hydrogen, and if you have a CO2 source already or a carbon source, then it's maybe 20% losses. If you have to take the carbon dioxide from the air, for example, by air capture, then you lose another 20% at least, at best. Then you have some for combustion, for compression or for liquefaction and transport, depends. 700 bars compression, maybe 10% losses. If you go to liquid hydrogen, you lose 1/3 of the energy in the liquefaction process, and then at the end you have a combustion engine with 25 to 30%, and all this has to be multiplied with each other. So you get to 16, 17% or something like this.
Okay,
so nevertheless, this is the downside of the thing. The advantages, there are for sure also advantages. The advantages is we can produce electricity where we have more sun or more wind. We can go to Saudi Arabia or to Chile or whatever, and there we get maybe 2.3 times, 2.4 times more. We get more energy from the same PV system per square meter at the end of the day. Once we have produced these e-fuels, we have also a long-term energy storage.
That's on the upside.
That's absolutely, because when we want to power the electric vehicles of what type ever with electricity, then we have to provide electricity also during times which we call Dunkelflauten, so periods of time where we have low solar radiation and almost no wind. So in the beginning of December 2022, we had such a period of 2 weeks, more or less, where there was almost no power generation from renewables. And there we will need anyway hydrogen as a long-term energy storage.
So a backup energy source.
Backup energy. So part of the energy has to go to hydrogen, and then from hydrogen back into electricity anyway, also for electric vehicles. So
out of political reasons, kind of, or like just seeing it globally, or not globally, but maybe on a national level, in order to provide the energy security. I think that's what you point out
absolutely. So the electricity sector needs significant backup capacities. This is very clear. From today's perspective, gas turbines, which can be operated at the beginning with methane, but should be able to switch over then to pure hydrogen at the end of the day. But for sure, this is only a relatively small share, which goes via the hydrogen, and therefore the overall efficiency is still high. So all these things need to be discussed at the end of the day. But nevertheless, even producing hydrogen or ammonia or whatever somewhere in Saudi Arabia is not for free. So therefore economics really matter, and we have to look carefully to this. This is for sure one of the big things in all these hydrogen discussions, because at this point in time when we always discuss about cost. Cost for power generation, for the electrolyzers, for transport, and so on. What we don't know at all are prices. So if you look to oil, for example, in Saudi Arabia, the production cost for a barrel of oil is $10, and the market price is $80 or something like this. So hydrogen will be a rare resource, and therefore the prices will be significantly above the cost for a while. Nice for those who produce.
I understand.
Good for the ramp up of the infrastructures and so on.
Yes.
But for sure, for those who have to pay.
So we see basically the same market mechanisms like in the oil industry in the future in terms of hydrogen, likely. Maybe
for the next 20 years.
Yes.
In the medium term or long term, I expect it's getting better because the number of countries which can produce hydrogen or their following projects
more than there's oil
absolutely
sources available.
Absolutely, because there are so many places in the world where we have sufficient wind and PV or solar radiation and wind potentials. So in the long run, I expect that we have more offers, and so prices could get closer to cost, but not within the next 20 years.
Okay. Yeah, we will see. So we were talking about efficiency, right? So we talked about the efficiency of e-fuels. Hydrogen will be a little bit above direct hydrogen use through fuel cells, above e-fuel use in terms of efficiency. And now we come to EVs and battery-powered vehicles. Where is the overall efficiency there?
So on the battery side, on the batteries, it depends on how fast you charge. If you charge at home, for example, with relatively low power, 11 kilowatt or something like this. Then
so what you can get out of a wall socket?
Yes, on a wall box, not from a socket. This is only 3.7 kilowatts, but from a wall box, three-phase, you can get 11 easy.
That's what I mean, like a three-phase system that you have
system
available at your home.
But 11 or 22 doesn't matter, but for the efficiency. But then the efficiency of the battery itself is above 95%. But then for sure you have additional losses. You have
so that is the cycle.
In like and out.
Okay.
So we're operating a stationary battery, 55 megawatt, and there the lithium-ion batteries have efficiencies in the range of 97% in and out.
Okay.
But then on top you have for sure the losses in the charger. You have the losses in the converter from the battery to the electric machine, which you have in the fuel cell as well. So the losses from electric power, DC AC converter, and an electric machine. These are the same losses you have in a fuel cell car or in a battery electric car. What you get on top is for sure the losses of the chargers. And this depends. Good chargers may have losses of 3 to 4%, but there are also bad chargers in the field, especially if they charge at very low power ratings, which have somewhat less efficiency.
Okay.
So roughly we say from the energy we have, let me say from a wind turbine, we can bring about 75% of the energy into the motion of the car. Some losses in the grid, some losses in the battery, some losses in the chargers and electric machines and so on, but an overall efficiency of about 75% is
until the energy touches the road, you could say.
Yeah.
Okay. But it's still impressive what technology can do there. I'm always amazed by
absolutely
by
no question.
The efficiency of the electric drivetrain. Yeah. Okay, so that said, there's a lot of potential, I think, that the battery technology has. And what we are trying to do, I think everyone that is working in the space and researching in the space right now is pushing this boundary. We talked earlier about the different applicational fields, that there are remote applications, or also heavy and large-scale machinery requires a lot of energy, does not have the opportunity to charge frequently, and therefore there is a certain boundary that is not met, and that will likely not be met very soon through battery technologies. And there the options like fuel cell, e-fuels, etc. may be applicable. But if we look at the mass in terms of overall required energy storage for mobility, but also beyond, also for home appliances, etc. Battery technology is a solution. I think that is kind of how we can sum up the discussion so far, right? Let's look at how we push the boundaries. And I think there we come directly to ISEA, your institute, and also you're our neighbors here, who's at eLab with the CARL. And yeah, I would just like to open up a discussion on how do you in your daily work, in your research, but also with industry, tackle all the different points in order to push the boundaries? And then the first question would then be, and I think it's a manifold question in that case, what are those different points on that front of optimization that we have in front of us?
Yeah, that's a very good question, very complex. But I think what sometimes is overlooked, the most relevant thing for introducing the new technologies is not so much pushing the technology boundaries, but is reducing the cost. If we look to the photovoltaics, for example, for the last 20 years, the efficiency raised only marginal, a little bit meanwhile in the last few years, but for about 15 years more or less you can see a straight line in the maximum efficiency.
20%, or where are we right now?
Yeah, 23% for monocrystalline on a 23% for monocrystalline cell. On a cell level, module is a little bit less, and so more or less. The theoretical limit for a single junction semiconductor is 30% efficiency in solar radiation. So then you would need different multi-junction cells or something like this. But nevertheless, this was not the important thing. But in a range or over a period of maybe 15 years, if you look to the world record lists for the silicon, for the crystalline silicon, the efficiencies almost did not increase. The reason is all the researchers, including the industry, focused on how can we bring down the cost. And this was extremely successful, much more successful than predicted by anybody. I'm still showing in lectures predictions of Greenpeace about electricity prices from PV, and I think we can be sure Greenpeace is a supporter of the technology on the optimistic side. At least a factor of 2 less expensive than they have predicted.
Yes.
And when the first feed-in tariffs have been granted, this was fortunately in Aachen. There were a price of 2 D-Mark, so €1 which was paid. For a kilowatt hour of electricity, and now if we go today on a free field installation, we have 5 to 6 euro cents, so a factor of 20 less. And this is what made the breakthrough of the technology. This made photovoltaics on a worldwide level to the most economic way to produce electricity today. There's no competing technology.
It's important to note. It's the most advanced technology in terms of price point.
Of price. That's the important thing. And this is what pushed the boundaries. And in batteries, first of all, it's quite similar. So for sure, we have still also increase in energy densities and so on. But what was most important to make it really applicable to electric vehicles is a reduction in prices. And here as well, in 2012, in 2012, the predictions by industry and others for 2020 were about 200 euros or dollars per kilowatt hour on cell level. In 2020. Actually, we were down to half, down to $100 per kilowatt hour.
And now we're going below it.
Right now, last year and this year, we had some increase because of raw material shortages, which is quite okay. But
the general trend,
the general trend is still going down, and we are getting rid of cobalt, and we have lithium iron phosphate, we have sodium-based batteries. They are all not better from a performance point of view. Lithium iron phosphate and sodium ion-based batteries will have significantly lower energy densities
than NMC-based cells.
Compared with NMC-based cells, right? But they have the chance to bring down the cell prices to $50 per kilowatt hour. And this is what opened the markets. Yeah? So this makes it possible to use the batteries everywhere. We have seen the same in the consumer products. The first lithium-ion batteries were sold for a price in the range of $3,000 per kilowatt hour. The first users were camcorders. So professionally used camcorders, because the camera persons were so happy to have
not to carry that much weight, right?
Exactly. Yeah. So because the lithium-ion battery offered immediately a reduction in weight by a factor of 2 compared with the nickel metal hydride or nickel cadmium technology. So people were happy to pay this, and then. Based on these first markets, the price decreased more and more. And then we switched over in laptops from nickel metal hydride to lithium-ion batteries. And then we came down further, and we were able to bring it into the cars. Because even at $100 on a cell or on the pack level, let me say, which we achieved by the end of the decade, surely, a 100 kilowatt hour battery, which we have in the upper class cars, is still 10,000 euros. Just for purchasing this battery. So this is not what you get as an end user, but as a car manufacturer.
There will be a margin put onto
sure. But so the only chance also when we talk about trucks and so on is if we bring down the price. And this is what we see in the market today. So we see on the one hand, for sure, increases in energy densities, but mainly because higher energy density also means lower price. So this because if you have a higher energy density, it simply means you need less raw materials for the same amount of energy. So exactly, or you have to produce less battery cells for the same energy, and this reduces prices. So increasing energy density is also a matter to reduce cost. But especially for the passenger cars, we don't need higher energy densities. So, and this is what you can see. What you can see very easily by looking that the lithium iron phosphate, for example, returned. So it's not a new technology.
It's a cheap technology.
It's a cheap technology.
Yes.
But the energy density. So with the NMC batteries, we get to 270, 280 watt hours per kilogram these days. With lithium iron phosphate, maybe to 180. So significantly less. But for the passenger cars, in the small and medium size, we have sufficient space, and the weight is not really a major issue.
I think that's one thing I want to point out in a second. But I think for the general listener, let's say, who thinks of, but the range of an electric vehicle is still, like, compared to a diesel, quite limited. And now you're saying it's not an issue. Can you explain how you mean that? Because I think it's important to note. I think you speak at it from a statistical, let's say, global point of view, that the average distance one has to travel is far, far below the maximum range a vehicle can achieve.
This is absolutely true, but this is not my main point. The main point is the range of the vehicles is limited by the cost of the battery. So that's a point. For sure, we can build even a smaller car with a range of 400 to 500 kilometers of driving range. But the question is there somebody who will buy this at the price? So I just mentioned 100 kilowatt hours of battery cost 10,000 euros just as cost for the manufacturer. So some years ago, the production of Volkswagen Polo was about 5,000 euros, and then the final sales price is 15 to 18,000, because for sure you need the margins, you need the taxes, but you need also all the development work and so on, R&D costs and so on. So this means 5,000 for the complete car, and now we're talking about 10,000 just for the battery. So the battery cost is what limits the driving range. And
determines then how much the capacity will be. Because
exactly,
you're limited by that.
Exactly.
And the question there is that, are we meeting the customer demands? From your, we're not market experts, of course, but
so for sure there is people have to change maybe a little bit the use habits of the cars. But the first of all, the question is, will be conventional cars in some years maybe even more expensive? So we now get CO2 price on the gasoline, which adds. We have additional exhaust regulations which make combustion engines more expensive and so on. So first of all, the question is which cars or maybe electric vehicles will be cheaper than conventional cars already in a couple of years, 2025, 26, 27 or something like this.
From a TCO, total cost of ownership perspective.
Total cost of ownership perspective, right. But, it is important to keep or to see this together with charging infrastructure. We already discussed the charging infrastructure to a certain extent, because if we go for this ultra-fast charging, so first of all for the upper class cars, we can return electric energy in 3 minutes for about 100 kilometers of driving range in today's cars. This you cannot charge the battery completely, no question. But let me say, roughly in 10 minutes, we can recharge 300 kilometers of driving range. And I don't think that this is really affecting the use too much.
I mean, 10 minutes is less than a lunch break that we were referencing
exactly.
earlier, right?
Yeah, exactly. Yeah. So this is the people should anyway do for other reasons breaks. And in addition, we see this if you look to the Tesla charging stations. So they have significantly lower charging power, so their charging periods are significantly longer. But the drivers and the others in the cars, what they are doing, they are working on their tablets, on their smartphones, and so on. So they are doing all the communication and with the digital devices. They are not able to do it while driving, and they have to do it anyway somewhere. So at the end of the day, they will not tell you, what was such a boring break in between. After 3-4 hours, having a break for using the digital devices is anyway quite well.
So the takeaway, maybe one has to experience this before one really can make complaints about it. I think that's kind of the point here, right?
I absolutely agree. Years ago I already said, don't put too much subsidies on the table. It would be much better if you give the people the opportunity to really experience this. Today, if you buy a car, maybe you are allowed to drive around for an hour or something like this, and then you decide. For an electric vehicle, you have to drive 2 weeks, 3 weeks or something like this to really experience, can you charge at home at the moment or where you work, or do you have other chargers in range? And some people will figure out at this point in time, no, there's not sufficient charging infrastructure. No question. But, we're talking at maximum of a rate of 80% of the new cars sold as battery electric vehicles in 2030. And today it's maybe 20 to 25%. So we're still selling a lot of non-electric vehicles. So it's not a problem at all if at this point in time some people decide, no, sorry, the charging infrastructure or the way how I use a car is not really perfect for electric driving at this point in time. No, that's not a problem.
But anyways, one really needs or should push in that direction, support the industry in case or if he's able to, right? Because we need the fast transition, maybe to come back to the 2-degree climate goal.
But one of the question is it feasible, or is it really the right way to force the government to set up the ultra-fast charging infrastructure, which was long time tried by European car manufacturers. Tesla did it from the very first day on their own, because they don't want it to wait for governments. And meanwhile, one or the other of the German car manufacturers have announced to invest into these charging infrastructures themselves. Also because I think this is a way to earn money in the future. They are
integrating that in their product portfolio currently, right?
But this leaves the problem with the smaller cars. The smaller cars do not have 500 kilometers of driving range, and you also cannot recharge in 3 minutes because then the C rates will be too high. Smaller batteries,
higher C rates,
and this is not really good. So the small, medium-sized cars, maybe with a range of 300, 350 kilometers, it's still for 95% of all users, that's by far sufficient. Yeah, it's maybe just a few trips for holidays, or if you visit parents or relatives or whatever, where you may need larger distance.
And plan in a little bit of time.
And then you have to plan it different.
I understand.
I have a car which just has 240 kilometers of driving range. Yeah? So this makes it necessary to have, when we go on holidays, somewhat different plannings. But we go in the morning for 220 kilometers, and we make a lunch break for 2 hours in a city, where we make a city walk and looking maybe into a museum. And then in the afternoon we have another 240 kilometers, and then we stay somewhere overnight. Yeah, so it's our holidays. We have time, and for the first time we see cities on the roads we just have passed on the highway in the past, and we have experienced cities we have never seen before, and which were great.
Yeah, it's also opportunities that emerge.
It's opportunities, exactly. Yeah, so if we just ask if things will exactly remain as they are, they won't. Yeah, so all these energy crises, the climate change, will result in some necessary changes in our habits. Yeah, so we try to keep them as low as possible. And the Technical University, as RWTH Aachen University, is surely dedicated to develop, to bring forward technology to keep things, let me say, as much as they are, as they have been in the past. But fuels for airplanes will never be that cheap again as digging oil, which was there some 100 million of years, or formed in some 100 million of years, and which we are now using up in 100 years.
Sure.
So the e-fuels will be more expensive. So it will not be that easy to just fly over for afternoon coffee to Barcelona and coming back in the evening. Yeah, so some things will change. So we have to be aware that we were using our world significantly more than we should. Yeah, so we use the resources 3 times more than we should at the moment.
Yeah.
Also, future technologies will not without any harm to the environment, no question. Mining for raw materials and batteries requires still mines, so no question. But if we can reduce the use of resources maybe to 1 instead of 3 times what is sustainable. At the moment we're using 3 times more resources than the Earth can rebuild. So if we bring it down to 1, then at least we already have won a lot. But to be honest, even the battery is not clean. So I never would say the battery is clean. It's cleaner than what we're doing today. But for sure, where you have the mines for cobalt or for lithium, it won't be nice for the environment right at this point in time.
Yeah, it will be not just a technological shift, but also a shift in our everyone's mindset to kind of meet in the middle, right? You mentioned like your holiday trip, which will be a little bit different than it used to be, but being creative about it, it will nevertheless be as enjoyable. And to offer everyone the experience, meaning that everyone can afford a vehicle, even may it be small, but to push in that direction, you mentioned we have to bring the cost down. I would just like to just briefly touch on your research and where the levers are. So what can we do in terms of technology innovation on the battery field in order to push the levers that have an impact on the cost decrease? Well, where are the big gains to make?
So what we're focusing on, first of all, is really increasing reliability and lifetime. For sure, if the battery can live as long as a car, we must not exchange it in between. This is a very important target because exchanging a battery after 8 to 10 years, which is significantly more expensive than the remaining value of the car, is something we should try to avoid. Also reliability for sure is very important because, as I said, if a battery fails maybe shortly after the warranty period is over, this is especially for those who buy small, medium-sized cars, this is a strategy, really a tragedy, because this means you have to pay huge amounts of money to replace this, or the car has to be replaced completely. So this is first of all where we try to get in. So the other thing is we try to support first of all also those who manufacture batteries. So by making quality controls and giving them fast feedback if the production processes they just apply can result in these long lifetimes.
So meaning raising the quality during production?
Raising the quality, but especially giving fast feedback. So, you can optimize a production process
That's what I mean.
If you have a feedback loop.
So you're giving feedback on about the product and kind of trying to connect the characteristics of the product or the properties. Can correlate them with the production process, meaning, hey, you have this temperature in your production process, or this pressure applied, or whatever, or like the gripper system, which may tear on the active material, for example, of the electrodes, and then you kind of try to provide feedback.
Whereas especially our work is not even saying it was this temperature or this specific process. We mainly can say, so what you have used as a process at this day resulted in a quality like this, and then the production specialists, they know best what they have done and where they can improve things.
So you're analyzing the product and giving clear statements about this is a fault on the product or could be optimized, and then creative people like, for example, also we at eLab here trying to optimize the production process.
Exactly. So we are not operating processing lines. So what can be optimized or what may have went wrong or something like this. This is really up to those who operate such lines, like in the eLab. Or in the research factory in Münster, or even Forschungsfabrik FFB, or even at the commercial manufacturers. So this is one side, but we also can provide for sure our colleagues from material research with feedback, because the idea is to assure.
So that's even upstream. The one is the recommendation downstream, and the other one, you're mentioning now, the material side, is the recommendation upstream.
Right. So especially to avoid that they are working too long on maybe materials which will not make a difference to the existing products. So we can compare them continuously with the state of the art. And at the end of the day, if you want to introduce a new material, you must have an idea to be either significantly cheaper, or cheaper than the existing product, or having a better performance. But if you cannot at least achieve theoretically one of those, then it's not the right way to work on. These answers are not simple, because for sure they can be very different in different applications. We talk about air taxis, for example. They have significantly different requirements compared with a passenger car. So the air taxi weight is really everything, and the passenger cars
weight doesn't really matter. The volumetric density,
volumetric energy density and performance and so on. So this means analyzing also new materials or new cell products requires really a multidimensional view on all the different types of applications to see, are there certain markets where the product could compete with the existing technologies or not. And then we can say, okay, maybe in this niche or in this market, this could be a competitive material or product. Try to optimize it for these purposes.
So there's not one size fits all in terms of battery research and optimization. And
not at all.
That makes it, I think, quite diverse, quite challenging sometimes, because you also have to understand the requirements first and right. What are the power requirements? What are the weight densities one has to achieve in order to reach? You mentioned the air taxi, in order to be able to fulfill that use case or deliver.
Absolutely. This is also why we're coming from engineering. So this is why we are in an engineering faculty. Because, as you said, first of all is understanding the applications. We talked about trucks, for example. So I was not really aware before we looked really into this that 90% of trucks on European roads are limited by their volume in cargo, not by weight. because we talked earlier about hydrogen or batteries, and there's no question that the hydrogen systems are significantly lighter than the batteries. This is not that's totally clear. The batteries are significantly more heavy. Yeah? But the most important thing for most of the trucks is volume. And the volumetric energy density, even of a 700 bars pressure hydrogen system, is not better than that of a battery. So there's no advantage. So from a logistic point of view, the hydrogen does not really bring advantages in terms of logistics. Just in case you switch over to liquefied hydrogen. Liquid hydrogen for sure is significantly lower volume compared with batteries and lower
but you have
weight.
Additional losses as well.
Another third of losses. And then we come back to the question of costs for energy and margins and so on. But it's extremely important to look into all these things very carefully, first of all. Also, if you say a truck must run 9 hours continuously, then the battery rules out. Too heavy, too much volume, too much weight.
It just must be too big then in order to fulfill the use case.
But if you have to make a break after 4.5 hours,
megawatt charging,
it works.
Yes,
it works.
Then we have the use case.
So this is exactly. So we have to look very carefully in these different applications. And we talked earlier on excavators or construction machines or farming machines. We need individual answers to each of these different fields, and this is extremely important. And we have to be open to all different technologies.
And that is why you founded CARL, right? The research center now that allows extensive testing on various different aspects on the optimization.
So we are based maybe on 3 main pillars. So one is really testing. We'll have over 5,000 test benches for batteries. So we can take in also from a commercial cells or whatever. But for example, when we work together with a production line, we can take in every day 10 cells, for example, as samples. Every day, 10 new cells, and then we can analyze them with computer tomographs and thermal imaging and electric testing, and then we bring them into lifetime testing for days, weeks, or months. And next day we get another 10, and then we produce a feedback. So this is the one pillar. The other is just doing testing takes much too long because batteries are good these days. So this means the aging is quite slow, but with all the analytics we have.
Good for the application, bad for the research.
Exactly. So this is exactly the point. For in the application, we are happy to achieve 10, 15 years of lifetime. But with all the analytics we have, from computer tomographs on a nanometer scale, electron microscopes, all the material analysis, we can see what happens to the materials much earlier than we really recognize change in internal resistance or in capacity. We can see if there are some layers are forming or corrosion happens or some crystals are breaking or whatever.
And all those what you're mentioning now, to put this back into perspective, is all having an influence on the cost in the end, or would you say that can one simplify it in this way? Or
two things. First of all, it allows to introduce products much faster. This is especially when we look to the challenges we are facing. So we really have to change the energy system and the mobility on a short time scale. And so one of our main targets is to really help to reduce the market introduction by a factor of 2. Because we can give data on reliability and so on much faster and earlier. Because even if you have developed the battery's material and then you make a cell, then you still have to convince a car manufacturer that he will not get problems after 5 years, after 8 years, or whatever with the batteries. So they need good basis for their decision to bring this into the field. That's a safe product and long-living product. So this is a one part. And the other, for sure, is increasing reliability, increasing lifetimes. This all reduces life cycle costs significantly. Yeah.
Okay.
And the for sure using new materials, for example, cobalt-free materials. The materials, first of all, have to come from those researchers or companies who are doing research on the material side. Yeah? So I cannot say CARL is reducing the cost by eliminating the cobalt. This has to be done first of all by somebody else, but we can check then if this product without the cobalt is really suited to bring it in certain applications. And if we can show these applications, then we can accelerate the pathway into this significantly. And this then will in the total. Yeah, so.
So that's the second pillar.
It's a second, the second pillar in our research is really the analytics. So the one is testing, there's analytics, and the third pillar is simulation.
Okay.
But if we look to the overall, then there we have the material research. On the one hand, we have the production, as we're doing in the eLab, on the other hand, and we are in between. Yeah, we are closing the gap between material on cells on the one hand, and from the products to the application. Yeah, so we are sitting there in between, and we all together, material research, production technologies, and what we are doing on bringing the products into the market. This all together reduces cost.
Okay,
but got it. It's not the production process on its own. It's not the material research. But this is, and I think especially we were able in Germany to set up a really good research infrastructure also here in North Rhine-Westphalia, having basic research, for example, at the research center in Jülich, but also in Münster. We have the fabrication production experience and expertise here in Aachen, and then also for the research factory in Münster. And we have all these topics we are looking for. Integration of the batteries into the applications, long lifetimes, and so on. And this all together really allows us to tackle the challenges we are facing. And I think, therefore, this is a very well designed setup, which can be hardly found in the same way as we have it here in North Rhine-Westphalia, with eLab in Aachen, with CARL in Aachen, with the Münster facilities, with Jülich facilities. This is it's really a big asset.
Yeah, it really sounds beautiful the way you put it, like a big family, a research family, an innovation family, so to speak.
Absolutely.
Couldn't have put it in better words. Professor Sauer, thank you very much. I think with this...
it was my pleasure.
We can look forward to the next conversation. But for now, thank you very much. I'm seeing forward to the next one.
Yeah, thank you very much. It was a nice talk, and all the best.
Thank you.
Thank you.